You wake up, your eyes are itchy, your nose is running. There's a pressure in your head that wasn't there when you went to sleep. You look outside and see a fine yellow dust coating everything, pollen, and just like that, another beautiful spring day is ruined. You reach for the antihistamines and wonder, for the thousandth time, why your body is so broken. Why does it launch a full-scale war against something as harmless as a speck of tree dust? It feels like a mistake, a design flaw. Surely, evolution should have weeded out this self-destructive tendency by now. But what if it's not a mistake at all? What if your seasonal suffering is actually the echo of an ancient survival strategy? Or what if your allergies are, in a strange way, a gift from the Neanderthals? It sounds like science fiction, but the story is written in our DNA. To understand it, we need to go back in time. Not just a few generations, but tens of thousands of years. We need to understand our immune system, our ancient cousins, in a world very different from our own. First, let's talk about the immune system itself. It's your body's military. Its job is to tell the difference between self and not self. It identifies invaders like bacteria, viruses, and parasites, and then it attacks them. It's a complex and brutal system designed to keep you alive in a world teeming with things that want to eat you from the inside out. When it works right, it's a masterpiece. A virus gets in and your immune cells recognize it. They create antibodies to tag it for destruction. Killer cells move in and eliminate the infected cells. You get a fever and feel sick for a few days, but you survive. Your body remembers the invader, so next time the response is even faster. An allergy is what happens when this system goes haywire. It's a case of mistaken identity. Your immune system sees a harmless protein like one from cat, dander, peanut, or pollen and treats it like a deadly parasitic worm. It panics. It mounts a massive, overwhelming defense against a non-existent threat. The main culprit in this overreaction is an antibody called immunoglobulin E, or IgE. In a normal immune response against a big parasite, IgE would be a hero. It would latch onto the worm and signal to specialized cells, called mast cells, to come and destroy it. Mast cells are like little chemical grenades. When they get the signal from IgE, they explode, releasing a flood of chemicals. One of the most famous of these is histamine. Histamine is the chemical that makes you miserable during an allergic reaction. It causes your blood vessels to leak, which leads to swelling and inflammation. It makes your nose produce tons of mucus to try and flush out the invader. It causes smooth muscles to contract, which can tighten your airways in an asthma attack. It makes you itch. All of these reactions would be useful if you were trying to expel a physical parasite from your body. But when the invader is just a cloud of invisible pollen, the reaction is pure, pointless misery. So the question remains, why would our bodies develop such a sensitive, trigger-happy system? For a long time, the leading idea was the hygiene hypothesis. This theory suggests that our modern world is too clean. We grow up in sanitized environments with less exposure to dirt, germs, and parasites than our ancestors. Our immune systems don't get the proper training they need in childhood. They are like bored soldiers with nothing to do, so they start picking fights with innocent bystanders like pollen. There's a lot of truth to this, but it might not be the whole story. The hygiene hypothesis explains the why now, but it doesn't fully explain the why at all. Why do we have this specific type of supersensitive immune response in the first place? The answer might lie with who we share our DNA with. To find that answer, we need to meet our family. For most of human history, we were not the only humans on the planet. Our species, Homo sapiens, evolved in Africa around 300,000 years ago. But other human species had already left Africa and populated the rest of the world. In Europe and Western Asia, there were the Neanderthals. They were not the brutish cavemen of cartoons. They were intelligent, sophisticated hunters. They made tools, controlled fire, buried their dead, and survived in the harsh Ice Age environments of Eurasia for hundreds of thousands of years. They were shorter and stockier than us, powerfully built and adapted to the cold. In Asia, there was another group, the Denisovans. We know much less about them. They are a ghost lineage, known to us almost entirely from a few fragments of bone and teeth found in a single cave in Siberia. But from those tiny fragments, scientists extracted a full genome. Their DNA tells us they were a distinct group related to Neanderthals, but on their own evolutionary path. For a very long time, these groups were separate. Our ancestors were in Africa, and the Neanderthals and Denisovans were in Eurasia. Their bodies and their immune systems were adapting to completely different environments, different climates, and different diseases. Then, somewhere around 60,000 to 100,000 years ago, a small group of our Homo sapiens ancestors began a massive journey. They migrated out of Africa. As they moved into the Middle East, Europe, and Asia, they walked into a new world. and they were not alone. They met the Neanderthals, they met the Denisovans. What happened when these different human groups met? For a long time, we thought they simply replaced them. The story was that the clever Homo sapiens outcompeted their cousins, who then faded into extinction. But the genetic revolution of the last 2 decades has shown us a much more intimate and complicated story. They didn't just compete, they interbred. When scientists first sequenced the Neanderthal genome, they compared it to the genomes of modern humans from around the world. They found something astonishing. Every person today with ancestry from outside of sub-Saharan Africa has Neanderthal DNA. It makes up about 1 to 4% of their genome. This means that at some point after leaving Africa, our ancestors had children with Neanderthals, and those children survived and passed their mixed DNA down through the generations, all the way to us. A similar story happened with the Denisovans. Traces of their DNA are found in many modern Asian populations and at particularly high levels in people from Melanesia, like Papua New Guinea, where it can be as high as 6%. This wasn't just a random one-off event. It was a crucial chapter in the human story. The DNA we inherited from these archaic humans wasn't just junk, it was functional. It affected our skin, our hair, and most importantly, our immune systems. And this is where we get back to your allergies. Think about the situation from our ancestors' perspective. They were newcomers in Eurasia. They had spent hundreds of thousands of years in Africa, and their immune systems were perfectly tuned to fight African pathogens. But Eurasia had a whole new set of bacteria, viruses, and parasites that they had never encountered. Their immune systems were naive, they would have been incredibly vulnerable. A simple infection could have wiped out entire groups. The Neanderthals and Denisovans, on the other hand, were the long-term residents. They had been living in Eurasia for over 300,000 years. Over countless generations, their immune systems had evolved and adapted to fight the local diseases. They had the right genetic tools to survive there. When our ancestors interbred with them, it was like getting a genetic shortcut. Instead of waiting thousands of years for their own immune systems to slowly adapt through random mutation and natural selection, they got a software update directly from the locals. They inherited fully functional, pre-adapted immune genes from the Neanderthals and Denisovans. This would have provided an immediate and powerful survival advantage. The children of these mixed unions would have been better equipped to fight off local infections. They would have been more likely to survive and have children of their own, passing on those helpful Neanderthal and Denisovan genes. Scientists have identified exactly which genes were passed on. A key group of these are called toll-like receptors, or TLRs. You can think of TLRs as the sentinels of the immune system. They sit on the surface of your cells and act as watchmen. They are designed to recognize the molecular patterns of invaders, like the proteins on the outside of a bacterium or the genetic material of a virus. When a TLR spots an intruder, it sounds the alarm, triggering the first wave of the immune response. It turns out that modern humans inherited several key variants of these TLR genes directly from Neanderthals and Denisovans. A specific cluster of them, TLR1, TLR6, and TLR10, shows clear Neanderthal ancestry. These genes are crucial for recognizing bacteria, fungi, and parasites. The Neanderthal versions of these genes were likely much more aggressive and sensitive than the African Homo sapiens versions. In the disease-ridden world of Ice Age Europe, that was a very good thing. A hypervigilant immune system was the difference between life and death. So our ancestors got this powerful immune system package. It helped them survive and thrive as they spread across the globe. It was a massive evolutionary success story, a gift. But gifts sometimes come with strings attached. The world has changed. The threats we face are different. The powerful immune response that was perfectly calibrated to fight off a parasitic worm infection in a Pleistocene hunter-gatherer is the very same response that is now overreacting to dust mites in your clean, modern bedroom. The genes that gave our ancestors a sensitive alarm system to detect real threats are now responsible for an alarm that goes off at the slightest provocation. The Neanderthal TLRs that were so good at recognizing the surface of a parasite might now be mistaking the similar-looking surface of a pollen grain for an ancient enemy. The aggressive response is the same, but the target is wrong. This is the mismatch. Our genes are ancient. They were forged in a world of constant, life-threatening infections. Our environment is modern. We have sanitation, clean water, and antibiotics. We are no longer swarming with the parasites that our immune systems evolved to fight. That powerful genetic weapon, inherited from our Neanderthal cousins, is now left with nothing to do. And so it turns on harmless things. It turns our own bodies against us. The evidence for this is more than just a good story. Our studies have shown a direct link between these specific Neanderthal-derived immune genes and a higher risk for allergies. People who carry the Neanderthal variants of the TLR gene cluster are more prone to hay fever and other allergic sensitivities. The very genes that once saved us are now making us sneeze. And it's probably not just allergies. An overactive immune system is a double-edged sword. It can also lead to autoimmune diseases, where the body's defenses mistakenly attack its own healthy tissues. Conditions like Crohn's disease, lupus, and type 1 diabetes are all linked to immune system dysfunction. It's plausible that our archaic inheritance contributes to our susceptibility to these modern illnesses as well. It's the price we pay for the ancient advantage. Of course, the story is not quite that simple. No single gene causes allergies. Our susceptibility is a complex mix of many different genes, our environment, our diet, and pure chance. Not everyone with Neanderthal DNA has allergies, and some people without these specific genes still do. The Neanderthal inheritance is just one piece of a very large and complicated puzzle. But it's a very important piece. It provides a deep evolutionary context for why our bodies act the way they do. It also changes how we might see our Neanderthal relatives. They are not some failed, extinct branch of the family tree. They live on inside us. Their genetic legacy is a fundamental part of who we are. Help make our survival possible. Every time you fight off a cold, you might be thanking a Neanderthal gene for its rapid response. And every time you sneeze from pollen, you are feeling the echo of that same powerful legacy. It's a profound idea. The struggles of our ancient ancestors are not distant history. They are active within our cells, influencing our health every single day. The world they lived in is gone, but the genetic tools they honed for survival are still with us. We are living with an immune system that was built for a world of mammoths and mud huts, not a world of office buildings and air filters. This perspective doesn't offer a cure for allergies. An antihistamine will still work better than contemplating your evolutionary past. But it offers a different kind of understanding. Your body isn't broken. It's not a flaw. It's a relic. It's running ancient software on modern hardware, and there are bound to be glitches. Your immune system is not trying to make you miserable. It's trying to protect you using the only rulebook it knows, a rulebook that was written tens of thousands of years ago in a hostile and dangerous world. The story of our DNA is a story of adaptation and trade-offs. The interbreeding between our ancestors and Neanderthals was a critical event that gave us an advantage. It helped us, the newcomers, to rapidly adapt to a new continent filled with new dangers. The cost of that rapid adaptation is a heightened sensitivity, an immune system that is sometimes too powerful for its own good in our modern, cleaner world. So, are allergies a gift from Neanderthals? Yes, in a way. They are the downside of a much bigger gift. The gift was survival. The gift was a set of genes that allowed our ancestors to endure and spread across the planet. The allergies we experience today are the unintended consequence, the faint, frustrating echo of that ancient, life-saving bargain. The next time you feel that familiar tickle in your nose, you can blame it on the pollen. But you can also think of it as a reminder of your deep, complex, and surprising human history. It's a connection to your long-lost cousins, who live on in the most intimate way possible as a part of you.